Okay, this is Unit 9, Day 2, Power Series. So you'll notice that we are going to kind of take some of the things from Unit 8 and combine them with this Taylor series, this new idea. So in a power series, you see this summation, again, kind of this from Unit 8, and we're saying this special type, if it is of this form, it's called a power series. So we have your first term, and then you have that integer, you have a linear term, you've got that quadratic term, and you kind of see this we called the center C when we were doing a Taylor. So for a power series centered at C, there are three possibilities. So one of these three things is going to be true. The series converges only at C. So we can find a value where it's going to converge, and it might only converge. It might only kind of overlap there at the center C. Or we can do a little bit better. So even better is if there exists some number R where it converges for things near that R and diverges when you're bigger than that R. So this R is going to be called the radius of convergence, meaning that it kind of overlaps, right? We can converge for an interval, but then after you get away from that radius, then it's going to diverge. Or the series converges for all numbers. You don't have to be kind of on that interval there, okay? So if the series converges only at C, if it only converges at the center, then the radius of convergence is 0, meaning you only converge at that one point and you don't converge anywhere on either side of it. And if it converges for all of x, then the radius of convergence is infinity. So think of it, if this is your center, you could either converge at the center, you can converge for some radius, right, maybe from there to there, or if it converges for all numbers, then your radius of convergence is infinity. Okay? So what we're going to do is we're going to have to recall some of those convergence tests, and especially the ratio test works really well with a lot of these examples. Okay? Remember that we do need to check the endpoints to see if the inequality symbol has if it is less than or equal to, or greater than or equal. So you need to kind of check to determine if you need to put in the line underneath your inequality. Okay? So let's just take a look then at the first example. So we have example 1 here. Okay? Find the radius of convergence and the interval of convergence. Be sure to check your endpoints. Okay. So again, we see this factorial, and that factorial reminds me that a ratio test is probably a good strategy. So I kind of start with that ratio test. And if you recall from your pink sheet, the ratio test says wherever you see an n, you replace it with an n plus 1. So we take the limit as n approaches infinity, okay? And we do the absolute value. We replace n with n plus 1, okay? So we have n plus 1 factorial, and then x minus 3 raised to the n plus 1, okay? So wherever there was an n, I put an n plus 1, and then it's divided by the original. So then I just recopy the original a sub n there. So one thing I want to make a point of noting here is notice that the limit is n approaches infinity. So n is our variable here. This is going to be a constant, okay? And that's going to be handy. So I'm going to go ahead and use those factorial rules to kind of clean this up or simplify it. So we can go ahead and clean this up. Remember, this means n plus 1 times n minus 1, right? And this is n times n minus 1 times n minus 2, and so on. So this is going to be completely gone, and I'll be left with an n plus 1. And remember, if you have the same base, you subtract the exponent, so n plus 1 minus n just leaves me with 1, so really it's x minus 3 to the first power. And I can drop my absolute value bars here because we're plugging in positive values for n. Okay, so now since n is what we're approaching, okay, this part is a constant, meaning the infinity, when I go to plug in infinity, that's not going to affect this part. So I'm actually going to rewrite this and pop it out front, okay? So I'm just going to rewrite it. That'll still have the absolute value bars because since n is going to be positive, I know that I don't have to worry about it there, but I do need to kind of worry about this. So I'm going to have the absolute value of that part, okay, because my variable is n. So I can guarantee that I'm plugging in positive values for n, but not really for this x. So I'm going to have this, the limit as n approaches infinity of just this n plus 1. And we know that now I can evaluate this piece would give me infinity. So this is infinity. Okay, well, infinity times this would just give me infinity, right? Well, then you have to kind of remind yourself what you're doing. Recall from that pink sheet, if you don't have it handy, that in a ratio test, we're trying to compute this limit and we're trying to compare it to the number 1. So here, infinity is greater than 1. And if that's the case, then you are diverging by ratio test. Okay, so it diverges by ratio test. Remember, for the ratio test to converge, we want whatever the limit is to be less than 1. And so if this diverges, that means, go back up to your 3 possibilities, that this only converges at the center. So only converges at center. Okay, so in other words, your radius of convergence would be 0. Okay, in your interval of convergence, the x values, the set of x values for which this converges, is actually not really a set. It's really just x equals 3 because that was the center. Okay, so you can kind of get that from there, and I'll just kind of remind you of this. So remember, it's of this form where c is a constant and you're centered at c. So you take the opposite of that number in there to get your value. Okay? All right, so now we're going to take a look at B. Okay, so we're setting up this ratio test again. So when I do this, I'm still going to take the limit as n approaches infinity. Absolute value, wherever I see an n, I replace it with an n plus 1. So you've got this to the n plus 1, okay, over n plus 1 quantity squared. Divided by the original means multiplied by the reciprocal of the original. So I've got that, and we have the absolute value there. Okay, so next I am just going to kind of clean that up using some algebra. So I still have the limit. I didn't take the limit yet. And when we go here, these are the same basis, so we subtract the exponents. So that's going to leave us with just the x plus 1. And then I can't reduce anything there, so I'm just going to recopy that over that. Okay, so I have the absolute value. And then we're going to kind of pull that same trick again, where since n is the variable, I leave that, and I'm going to pull this out front, still in the absolute value bars. So this is going to be the same thing as the absolute value of x plus 1, then the limit as n approaches infinity, and then I've still got what's left in there is the n squared over n plus 1 squared, okay? Absolute value. Well, now I'm taking the limit as n approaches infinity. That's just using your horizontal asymptote rules, right? If I FOILed this out, I'd have it n squared. So I'd have n squared over n squared. That's just 1, right? The coefficients there are 1, so that you could think of this as balanced, your HA rules, however you need to do it. But you're going to end up with the absolute value of x plus 1 still out front. Then I get a 1 there. Again, that 1 comes from when I actually take this limit. It's your HA rules there. Okay. So then you kind of get to that point where you're like, wait, what am I doing again? You're doing a ratio test. The ratio test says that you converge if, when you take the limit as n approaches infinity of all this stuff, if you get something that's less than 1. So you kind of have to ask yourself, like before, it diverged, right? Like I got an infinity, so I knew that diverged right away. But this converges, okay, if this is less than 1. So times 1 is that. So I want that if that is less than 1. Well, I need to then find the value of x, or values of x, that make this true. Okay? So what you're going to do is solve an absolute value. You might remember from Algebra 2 to undo an absolute value. You set it up like this. You say -1 less than x plus 1 less than 1, right? You just make that negative on the other side. and you solve it. Whatever you do to the middle, you have to do to each side. So if you subtract 1 here, you need to subtract 1 and subtract 1. So that means that that equation up here, this inequality, is true when x is between, oops, this isn't negative 2, sorry. When x is between negative 2 and 0. And now this is what I mean by the check the endpoints, and this will help you on those multiple choice questions as well. So I need to determine, what's going on at negative 2 and what's going on at 0, okay? I know that this is centered at negative 1 because of this up here, right? So my center is at negative 1. So I want you to kind of imagine, like, I don't know, if there's 0, right? So negative 1 is here. I know that I'm going to converge there. And I'm now concerned about negative 2 and at 0. And I'm trying to find this radius of convergence. So I converge here. Now, do I get to include a closed circle or open circle at each of those spots? So like right now, I have it both open. So for any value between negative 2 and 0, I know if I plug it in that I'll converge. Well, what about if I plug in 2 and 0? I basically say, can I make this a closed circle? So to do that, you take that negative 2 and you plug it back into this summation up here. So I'll just say check endpoints. Okay? So I'm checking, I just say something like at x equals negative 2. Okay? When I plug in a negative 2 into there, I have the summation from 1 to infinity. And now be very careful. Guys, x is negative 2. It doesn't say anything about n. It says x is negative 2. So when I plug in a negative 2 there, I get negative 2 plus 1 is a negative 1 raised to the n over n squared. Well, now look what you have here. That is an alternating series. So now you need to use your alternating series test to determine if this converges, because if it converges at negative 2, then I can go back here and close that in, aka I can put the line under that to say it's less than or equal to. Okay? So I kind of check my alternating series test right here. Is this alternating? If you started plugging in values, you would see that it's alternating. It's decreasing in magnitude because as n gets really big, the overall fraction gets small. Okay? So then I need to take the limit as n approaches infinity of this thing. I'm just going to call it a sub n because I'm running out of room here. Okay? But when I take the limit of this, remember, negative 1 to the n is either going to be plus or minus 1. Right? And then in the denominator, when you plug in infinity there, you get infinity. So positive 1 divided by infinity or negative 1 divided by infinity equals 0. Now you need to recall your alternating series test conditions for convergence. It says that if you're alternating, decreasing in magnitude, and the limit as n approaches infinity is 0, then it converges. So therefore, converges by AST. So x equals negative 2 should be included. Okay, included. Meaning I'm going to go back here and I'm going to darken that in. Okay? And that means I can go ahead and make that there. Okay, that was only one endpoint. Now you need to go and check the other. So for this one, I do the same thing with 0. I take 0 and I plug it in for x. Okay? So at x equals 0, okay, I end up with the summation. It's going to be 1 to the n over n squared, right? Because if x equals 0, it's just 1 to the n. Guys, 1 to the n is just 1. So really, that's the same thing as the summation of 1 over n. And we know that that's the harmonic series that diverges, right? Diverges by, you could say harmonic, or you could just say p-series test. So because this diverges, I leave this open. Okay, because that diverges over here, that 0 is not included in the interval of convergence. Okay, so to answer my question, right, I got to kind of go back. I didn't really answer this question because it says find the radius of convergence. Well, my radius of convergence is 1, okay, because from negative 1 to negative 2 is 1, right? This distance is 1. This distance is 1. So the radius, meaning the distance on either side from the center that this converges, is 1. So I have a radius of convergence equals 1, okay? And this is centered at negative 1 And again, I know that that -2 is included. Okay? So that is some power series. Let me see if there's another example we'd like to do together. Okay, so on this example, I'm again going to be using ratio test. So if it says find the interval of convergence, ratio test is a great place to start. So here I am going to take the limit as we approach infinity. I'm replacing all the n's with n plus 1s. Here it involves a little bit more algebra. Okay, so after I cleaned it up with algebra, you get to this point here. And this is the point where you have to say, all right, n is the variable. So I can kind of reduce things, or kind of clean them up. And then I want to be able to factor out the x things, because the n is what's approaching infinity. So any of this x stuff that I can clean up, I want to take out. Okay? Recall in this one that -1 to the first power, right? That's just negative. So if I'm taking the absolute value of it, that's why that went away. Okay? -1 to the first power is -1, but we have the absolute value, so it's just going to be 1. And now I'm going to take this, pop it out front. Okay? So now I'm taking the limit as n approaches infinity over here. You can use your horizontal asymptote rules. So we factor that out, and your HA rules here. We have, this is bigger in the denominator, right? This would be a degree 2 in the denominator there. So this limit is 0. So 0 times that x squared gives you 0. Again, we're doing our ratio test. So we're saying 0 is less than 1, therefore it converges. This means that it converges for all x. So our radius of convergence is infinity. Our interval of convergence, right? You're going to be converging for any value of x. So I just wanted to finish up with just a couple things. Remember from last class, we had really messed with the sign of x. So we can write this as the summation for this general term here. These are the three that are most popular. The ln one shows up as well. I can give you that one as well. But you're definitely going to want to make a note of these, because then what we can do is we're going to be able to start manipulating these to be able to take integrals and substitute and things like that. But one question that had come up, someone said, looking back at this one, they said, why did you use ratio test and not an alternating series? I saw a -1, so I wanted to use alternating series. And so I just wanted to address that. You're going to want to use ratio test for a lot of these, because watch what happens here. So could we use alternating series? Yes, it's alternating. It is decreasing in magnitude. The problem becomes when you take the limit as x as you approach infinity there, right? Because now when you're plugging in, now you've got two variables. So that gets tricky, and that's why ratio test would work better. Okay? So I'm going to kind of stop this video there, and I can do a part 2 for the next part, because we're actually going to start manipulating. Have a great day.